So usually we just ignore it, but it's still there. Okay, great. What can I get over here? Well, what's functioning as my position here? Well, you tell me what's functioning in the place of position here. What is over there? Charge. Yep. What's functioning in the place of velocity? Current. It's not. I'm not saying charge is a position. I'm saying in these two equations they're playing the same roles. So I solve this for position. I can solve this for charge. Q as a function of t, and what are they going to call it? Yep. They're going to call it Q naught, or I'll call it capital Q, because that's the convention they use for the full charge on the capacitor. This is the full charge on the capacitor. Q cosine omega t plus phi. Phi always has to be there for general purposes. Same idea. The charge on the capacitor at any time is Q, the full charge, cosine omega t plus phi. Notice what this does. The argument of that function, actually that's not true. The argument can range however it wants to. That function, cosine omega t plus phi, ranges between 1 and -1. Which tells you that at some point you get the full charge, at some point you get minus the full charge. That's when it's flipped polarity, right? And at other times it's somewhere in between them, right? How did I get the velocity equation from this? Well, I just took the derivative with respect to time. You're going to get the derivative, you're going to get a minus sign from the cosine. Chain rule gives you an omega. So you get minus a omega sine omega t plus phi. Same thing here. How do I get the current as a function of time? I take a time derivative. I'm going to get minus q omega sine omega t plus phi. Right? I can get the acceleration here. If I took another derivative, there's nothing really I need to do with that here, but you could if you wanted to. Right? Same thing. So if you remember this, this is the same thing. If you don't remember this, it's a good chance to repeat it. Function's exactly the same. Any questions about any of that? Okay. So, if I then, which you probably did in 1600, graphed the position as a function of time. Assuming that you were starting off from your maximum displacement. You got something that looked like that, right? So on and so forth. Okay. You're going to get the same thing with this system, only instead of position, it's now a charge as a function of time. It's going to oscillate back and forth forever. The current will be the same thing, just with a sine function, right? It'll be shifted over by a 90-degree phase shift here, right? But you're going to get this thing that oscillates forever. Now, I'll do two graphs. What happened when I added friction to the system? Say that word again. Damp? Well, okay. Almost. This is an English thing. Damping, right? Not, and I'm not picking on you, we've all done this. This is what happens when you throw water on your system. This is what happens when you damp out the oscillations, right? It's a weird English thing, right? Yeah, it's not dampening, it's damping. You will find professors that say this word. I get it, I've said it too. But the actual word is damping. Something that takes up vibration is called a damper. And if you play piano, you have a damper pedal. That's what that thing does. It lets your strings vibrate, so on and so forth. Right, damping. What does damping do? Well, it takes energy out of the system. And so what you had, at least one possible scenario, is you had this. Where this, what we saw, the cosine function, now the displacement slowly gets smaller and smaller and smaller. In point of fact, it decays as an exponential. What do I mean by that? It means that there's an envelope function not draw that very well. But the envelope function here shows that there's a decay. When you envelop a function, mathematically this means you're forming the product of two functions. And so what this looks like, the form of this would be x of t is equal to e to the something times cosine of the something, right? Where this cosine of the something was what we saw a while ago, omega t plus phi. And the envelope then represents the decay. But what happened is the oscillation frequency now has to take into account the friction. This is only one possible method, or it's one possible outcome. Anybody remember what this one was called? What case? You have three different cases that could happen here. This is actually called the underdamped case, where there is still an oscillation, right? So you can think of this as taking this mass on a spring and just adding some friction to the system. It goes back and forth, but it just kind of slowly peters out. But if you take that same system and you dampen it, right, you put it in water, you just put it under water, it might not even get past equilibrium. It might just go to the equilibrium position and stop, right? It depends on how much resistance you have. So that would, I'm going to graph in a second, that would just be called the critically damped case, where there are no oscillations. Like that's the whole point. You never get past equilibrium, you just go to equilibrium and you stop. There are no oscillations. That's critically damped. Now you can do the same thing, but instead of putting it in water, maybe put it in molasses, right? It just creeps, right? It never actually, I mean, it might get to the equilibrium, it takes forever. That's called the overdamped case. Right? So you have three cases. Underdamped, which you have oscillations, critically damped, where you have no oscillations, and overdamped, where you really have oscillations. Okay. Something similar will happen to, in the system we're actually talking about, the LC system. Sorry. This is no longer an LC system, right? How do I take energy out of my electrical system? I put in friction for mechanical. What do I put in for electrical? Resistance. So now I have RLC systems. I have this same circuit, but now I'm recognizing that this itself is a simplification, and I've got to have some sort of resistance. What happens when I do that? Well, you have a more complicated differential equation to solve, basically. What comes out of that, which is a little bit beyond the scope of this course, it's actually quite a bit beyond the scope of this course, but if you keep classes for details. You have a system, which I'm going to give you this equation, although I don't really ever use this. Charge on capacitor is a function of time. They're going to use the uppercase. Your book uses a lowercase q on, but their own convention says to use the uppercase q. So it's the initial charge on the capacitor. E to the minus RT over 2L cosine omega t plus phi. So here's the envelope, right? This is what we expect, the oscillation. We get it, but it's enveloped by this function, the decaying exponential. We get an oscillation frequency out of this. That is this. This is all under a radical. 1 over LC minus R over 2L. That quantity is squared. Make sure we all know that this is an L. There we go. There we go. That's your oscillation frequency. So this is what it was without the resistor, but now I have this other term creeping in here, which comes right out of the solution to the second order differential equation for art with the resistance in it, right? So this is your energy bleeding term. This is your standard frequency, right? Okay. Let's think about our two cases. Now, think about our three cases, right? The first one I said was the underdamped case. What was the hallmark of that? There are oscillations, right? So if there are oscillations, there clearly is an oscillation frequency. What that has to mean, because this is under a radical, underdamped, greater than R over 2L squared. Why does that have to be the case? Because if it's not greater than that, then you get some sort of non-positive number in the radical, right? But as long as you meet this criterion, you get a positive number in the radical. Take the square root, no big deal. That's your oscillation frequency. This is the underdamped case. Okay. Now, critically damped. What did I say? There are no oscillations. So what's your oscillation frequency? 0. Critical damping. Will occur when one over LC equals R over 2L quantity squared. That's your critical damping parameter. It just comes back to equilibrium, does not oscillate. That leaves one other possibility. Overdamped. This is the case with imaginary solutions. What that means is 1 over LC is less than R over 2L squared. So those are the 3 possible cases of damping. So, why do we care? Well, what I said with when we're doing RC circuits is that they're pretty critical in timing circuits, right? If you want to have a circuit that passes through certain parameters in set amounts of time, make it an RC circuit. But now, what we have to recognize is there's no such thing as just an RC circuit. Because every circuit has natural resistance. Okay, I should say, let's start from me. There's no such thing as just a C circuit, because every circuit has resistance. Therefore, every circuit is naturally an RC circuit. Now we have to say, there's no such thing as just an RC circuit, because every circuit has self-inductance. So every circuit is actually an RLC. Well, every circuit with a capacitor, I should say, is an RLC. You can't have a circuit without a capacitance. You can't have one without resistance or inductance unless you're doing superconductivity, and we're not, right? RLC circuits. So if you're building a timing circuit, this is what you have to deal with. And so these parameters turn out to be really, really critical, right? Knowing whether you need to overdamp, underdamp, or critically damp something turn out to be, from an engineering perspective, important parameter. So, first situation with just the LC, energy is conserved, bounces back and forth between the charge on the conductor and the field. I should say the field in the I said conductor. Let me start that over. With just an LC, energy is conserved, bounces back between the field in the capacitor and the field in the inductor. RLC, energy is not conserved, stored in the fields in both the capacitor and the inductor, but bleeds out due to losses with resistance. Questions about any of that? Okay. For the purposes of what I want you to do with this, I mean, really, there's a lot of talking, but what can you do with this is not much, right? That's not what you can do with this is not that complicated, right? What's the charge on this circuit at this amount of time? Well, if you know all the parameters, that is, you know R and L, you can find everything in here. That's just plug and chug. More probable, I would ask you to determine a system given these parameters is overdamped, underdamped, critically damped, right? Just form this, find out what it is. Conceptually, I would love to ask you questions about the energy stored and where it is stored. So any questions about this, what I expect out of this, what you can do with it? Alright, one last thing to talk about in chapter 14, which is, this is a formula to show you, the energy stored in a magnetic field, right? So, we had, when we talked about the energy on a capacitor, as I said a while ago, we talked about where is that energy? We decided to store it in the field. And we had this expression for the energy in a capacitor. We also had another one for the energy density of the field. And what we came up with was density, energy per unit volume. We have this. Right? Where this is the C, of course, is Coulomb. So anytime anything Coulomb is electric, so you have your electric permittivity, you have your E field, and then the 1/2 comes as part of some calculus. We're not deriving it, we're just giving it to you. Okay. Same idea. Energy density in the, your book uses N here. Yeah. I'm used to using a B. Remember, the magnetic field is B, so I think that's pretty obvious. We'll stick with B. The magnetic field energy density in the inductor